In this lecture, we'll discuss on the test that one can do for checking the observability or constructibility of causal linear time invariant systems. For this, consider the system shown here, which is x dot equal to ax plus bu and y equal to cx plus du. ABCD are constant matrices, real matrices of appropriate dimension. The dual system of this particular system is shown in 2. From the duality for LTI systems, we already know that the pair AB for system 1 is reachable if and only if the pair A transpose B transpose for system 2 is observable. Similarly, the pair AB for system 1 is controllable if and only if the pair A transpose B transpose for system 2 is constructible. The pair AC for system 1 is observable if and only if the pair A transpose C transpose is reachable for system 2, and again the pair AC is constructible if and only if the pair A transpose C transpose for system 2 is controllable. So this is what we had seen from the duality for LTI system. Also for LTI systems, reachability implies controllability and vice versa. So if the pair AB is controllable for the LTI system shown in 1, then the pair A transpose B transpose will be observable for the LTI system shown in 2. Okay, for the dual system. Similarly, if the pair AC for the system 1 has to be observable, then the pair A transpose C transpose for the dual system shown in 2 would be actually controllable. Okay, so we'll rely on this to get a condition for identifying or for testing whether a given pair AC is going to be observable or not for causal LTI systems. Okay, so we'll use the controllability conditions to come up with the observability conditions. Okay, now since we know that A transpose C transpose being controllable implies AC is observable, so why don't we form a controllability matrix out of A transpose C transpose? Okay, so AC to be observable, A transpose C transpose has to be controllable. So what you do is you form a controllability matrix out of the pair A transpose C transpose. We'll denote this controllability matrix as QO transpose. Okay, so the controllability matrix shown here is C transpose, A transpose C transpose, A transpose square C transpose, and so on till A transpose to the power n minus 1 C transpose. Now for the pair A transpose C transpose to be controllable, this QO transpose has to have a rank n. If it has a rank n, then A transpose C transpose is controllable, which means the pair AC is observable. If QO transpose is rank deficit, that is the rank is less than n, then in such a case, the AC pair will not be observable. It will be unobservable. Okay. And checking the rank of QO transpose is same as checking the rank for the matrix QO, which is given by this column matrix, which is C, CA square till CA and minus 1. And this particular matrix here is also known as the observability matrix. So the controllability matrix for system 1 would be found from A and B. The observability matrix for the system 1 would be found from A and C as shown here. So what we essentially do for observability test is we form the observability matrix for the given CLTI system and we check the rank of this observability matrix. If the rank of this observability matrix is equal to n, which is the number of states used in the state space representation for the CLTI system, then the system, the pair AC is observable, or rather we can say the system in hand is observable. If the observability matrix is rank deficit, then the system will not be observable. It will be unobservable. So certain states might not be. We cannot possibly estimate them from the output that we have. Okay. Similarly, the PBS test that we had for controllability can also be extended to check the observability of LTI systems. Okay, so how do you do that? You calculate all the eigenvalues of the matrix A and check the rank of this augmented matrix A minus lambda I C. If the rank of this matrix is n for all the eigenvalues of A, then the pair AC is observable. Okay. If not, then the pair AC is unobservable. What I request you to check is what will happen to the eigenvector test that we use for controllability. How does it come here, or how does it apply here when we want to use it for observability analysis? So we'll stop here. Thank you.